lesson 8.3 is more looking at graphs and how graphs look. But we're not so much going to be looking at the actual graphs themselves. We're going to be looking at certain characteristics of the graph and how we find those. So we're going to be looking at asymptotes, how we know an equation has asymptotes and what those asymptotes are. So we're going to be looking at vertical asymptotes, horizontal asymptotes, and something called poles. And really just, it's not even that we're graphing them today, although I may show you what they look like on the graphing calculator, but it's how does the equation tell us these things? What are our clues? Okay? So, on this side, we're just going to go through a little bit of information. I'm going to try and explain this chart. If I recall correctly, there's a formula page you get. I have to make more copies before I can hand it out. But there's a formula page you get on the quiz, and on it I have the direct and inverse variation equations. And then the other thing I have is this chart right here. So if you understand how to use this chart and what it all means, you'll be good. You'll have the information, the reminder of how you find certain asymptotes and whatever. So, vertical asymptotes. First of all, we talked yesterday, right? Vertical asymptotes are always x equals a number. It's wherever it crosses the x-axis, so it's x equal a number is your vertical asymptote. Don't just give me the number, give it to me as x equals. And notice, how does it say we find vertical asymptotes? We find them by setting the denominator equal to 0. So take that bottom piece of the fraction, set it equal to 0, and that's going to give you a vertical asymptote. That's going to tell us where it is. The reasoning there, officially the denominator can never equal 0, right? When this denominator equals 0, this fraction ceases to exist. And that's exactly what happens with a vertical asymptote. Your graph doesn't exist there. And so, for example, if I take my denominator here and set it equal to 0, 3x minus 1 equals 0, how do we solve that? You're going to add 1 to the other side, right? So you'd have 3x equal 1, and then you will divide by 3. And x is 1/3. That x is 1/3 is an example of a vertical asymptote. Okay? Vertical asymptote doesn't have to be at a whole number. It's at a fraction in this case, and that's okay. So that's an example of how you find a vertical asymptote. Now, trying to remember here. A little bit of vocabulary I need to throw in that we talk about is that an asymptote. Do you guys know what I mean when I say a graph is continuous?
Continuous forever.
Okay, continuous forever means if I'm drawing this graph, do I ever have to pick up my writing utensil? No, a continuous graph, you never pick up your writing utensil, you just keep drawing, right? Well, if there's a vertical asymptote, like yesterday, on those graphs we did yesterday with the 2 separate curves, can you draw that? Is that continuous? Can you draw that whole graph, both pieces of it, without picking up your writing utensil? No, you're going to have to pick up that pencil, aren't you? Because you're going to have to draw one curve, jump over the vertical asymptote, and draw the other curve. So a vertical asymptote is what we call a point of discontinuity, because it's a point where the graph is not continuous, or discontinuous, if you will. And so, again, vocabulary here, a vertical asymptote, I'm going to write this in, is a point of discontinuity. Sorry, that's one of those words that takes me a moment to spell. Okay, so it's a point of discontinuity, and points of discontinuity can be removable or non-removable. A vertical asymptote is a non-removable point of discontinuity. Okay. Okay, you'll want to have this information, so there'll be questions about it in homework if I recall correctly. I like to think that a vertical asymptote, that's not something you can easily fix. That's a big old break in the graph, right? My graph is doing two different things on either side of it. It's not like I can just plug a hole, which will make sense when I talk about holes in a moment. It is two separate pieces. So it's non-removable. I think non-fixable is what I put in my brain. You'll have to find your own way to connect. But there's your information there. Okay? So that's a vertical asymptote. Now, we also have been talking about horizontal asymptotes, right? We've had both in our graphs. A horizontal asymptote, well, just like yesterday, horizontal asymptote is always y equals a number because it's where it crosses the y-axis at a certain number. Now, this one's a little different with how we find it. And notice it says, found by analyzing the biggest powers on top and bottom. Okay? We're going to analyze the biggest powers on top of the fraction and on bottom of the fraction. And that's going to tell me what to do here. So, and when we talk about powers, we're talking about exponents, right? So as we look at exponents, okay, if the biggest power is on bottom, then y equals 0 is your asymptote. Those are the ones we had yesterday. Okay. Those are several of the ones we had yesterday where the biggest power was on bottom. We had y equals 0. If the biggest powers match, so if your highest exponent on top and your highest exponent on bottom match, okay, so if the biggest powers on top and bottom match, it's y equals the ratio of those coefficients. And I think I have an explanation on that in the ones we do in okay. For example, let me use a quick example here. If you have, let me make something up on the fly here. Okay, can you read that? That says 3x squared plus 2x plus 4 over 5x squared minus 1. What are the biggest powers here? The biggest powers are the squares, yes? So those are the terms we're looking at. The rest of this doesn't matter when we're looking at horizontal asymptotes, okay? We only look at the biggest powers. In this case, my biggest powers match, right? X squared and x squared. So if my bigger powers match, x squared and x squared, the ratio of the coefficients, what are the coefficients of those terms? 3/5. And so for this example, it would be y equals 3/5 would be your horizontal asymptote based on that just random made up example. Okay? If the biggest power is on bottom, it's just y equals 0. If the powers match, it's the coefficients. And the third example, or third option, there's a possibility there are no horizontal asymptotes. And when are there no horizontal asymptotes? If the biggest power is on top. Look at my given example up at the top of this section. The given example was 3x cubed plus 2x squared over 3x minus 1. What's the biggest power on top?
Cube.
3x cubed. What's the biggest power on bottom?
1.
X to the first, right? Where's the biggest power?
Bottom.
Now, my biggest power is on top. So what does that fall into? That falls into this category of no asymptotes because the biggest power is on top. Okay? If this problem had been upside down and the biggest power is on bottom, it'd be y equals 0. So those are some examples. And as I said, we're going to do a couple examples on the backside, right? Okay. One more piece here, and that is holes. Okay, you understand what a vertical asymptote is. You understand what a horizontal asymptote. A hole is another break in the graph, but it's not like a big old break. A hole is the idea of I'm drawing. There's a hole. It's just a tiny little break in the graph. Now, on my graphing calculator, if I zoom in enough, I might see that. A lot of times when we as humans draw holes, we put an actual little circle there to represent the hole. But it's just a break in the graph where the graph doesn't exist at that point. A hole is always going to be x equals a number, just like a vertical asymptote. And holes occur if the functions on top and bottom can factor and reduce. So if there is a factor that can cancel out, there's a hole with that factor. And again, I'll talk about that in an example on the backside, but there is a hole if a factor can reduce. Now, earlier, a vertical asymptote was a point of discontinuity because it was a break in the graph, right? I had to pick my pencil up to draw it. Guess what? A hole? Officially, I had to pick up my pen to draw that, didn't I? Okay? I couldn't just keep drawing and have that hole be there. So a hole is also, gosh darn it, a point of discontinuity. And it's, instead of a non-removable, this one is a removable point of discontinuity. Okay? It's removable. The weird way my brain thinks, I think it's, okay, it's fixable. I can plug a hole, right? So, like, I can remove the piece, the hole, or I can put it back in. So I think, removable. I can remove a hole. So removable versus non-removable. Again, there's questions in homework, at least if I'm recalling correctly, about discontinuity and removable, non-removable. Before I turn the page, it wasn't here in the original notes, but I've since added it. They also talk about domain. Okay. So one of the topics, and I'm going to add it right here in your notes so you have the information about it. You'll just have to refer back to the front side. What kind of statement did our domain read like yesterday?
X.
It wasn't just x equals, though. All reals except x equals. And that x equals was my vertical asymptote, wasn't it? Okay, so my domain here is going to be all reals except any vertical asymptotes or holes. And so that's what I'm going to put for you so you have an idea. It's all reals except vertical asymptotes and holes. Forgot how much they include in these examples here. One other thing before I flip. Sorry. X and Y intercepts. Okay. We're also going to talk about X and Y intercepts. So, X-intercepts. Well, X-intercepts happen when Y equals 0. Now, the easiest way to find an X-intercept when you have a fraction is to set your numerator. You know what I mean when I say numerator, right? Numerator is the top of the fraction. We'll be setting our numerator equal to 0. And Y-intercepts, last thing, I promise. Y-intercepts happen when X equals 0. And so for Y-intercepts, we'll just put 0 in for X and see what it works out to be. So I'm just going to say let X equal 0. Lots of information, but this is kind of your reference section. Everything we're going to do in the notes and homework is going to be referenced right here. So this is where you'll come back to when I say, okay, how do we find this? How do we find that? This is what I want you coming back to. I'm ready to turn the page down, so I know I kept forcing some of you to not turn the page, so we got what we need. Okay. The examples ask us to identify all horizontal asymptotes, vertical asymptotes, and holes for each function. Well, to be honest, we're going to do those three things, and we're also going to talk about domain and X and Y intercepts because those are asked in homework. And so I'm trying to do, a good job at prepping you for what you're going to see in homework. Now, as we start with asymptotes and holes, notice it gives us a hint up here. And this hint is good. It suggests that we go in this order. That when we start asking ourselves questions, we start by asking ourselves if there's any holes. Then, after we decide if there's any holes, then we ask ourselves if there's any vertical asymptotes. And then after vertical asymptotes, then we'll ask ourselves, are there any horizontal asymptotes? Honestly, horizontal asymptotes can be done at any point. The key is to always check holes before vertical asymptotes is a good rule to follow there. So, with that in mind, first question we're going to ask ourselves, are there any holes? Okay. I see people starting to flip back because you've already long since forgotten how do we find holes? So if I flip back here, holes occur if the functions on top and bottom can factor and reduce. So, okay, factor. We need to start by factoring this problem. In this fraction, what do you see that factors? What are we saying? Well, we can't cancel the 3's. We have to factor first. And if you will recall, in order to cancel a factor, it has to be pieces that are multiplied together. Okay, we can't cancel pieces that add and subtract. Okay, those add and subtracted pieces are married. They can't be canceled. So we have to think in terms of factoring. And in order to think in terms of factoring here, first of all, my numerator of x plus 3, the only thing I can think there is there a GCF. And there's no GCF. My denominator factors. Dig deep in those brains, it's in there. X squared plus x squared minus 4x plus 3. It factors, not by a GCF, but we have a certain technique we use. You remember?
It would be x minus 3, x minus 1.
Okay, what's our technique here? Because that's what I'm looking for. Do you remember breaking this up? And we're doing product and sum. As I said, dig deep. It's in those brains. We've done it this year.
What is it?
If you might, here. Thank you. Okay, so x squared minus 4x plus 3 factors into two parentheses. X squared, I already heard you guys saying it. X squared breaks into x and x. Okay, my numbers have to multiply to be 3 and add to be negative 4. I'm ringing bells, right? It's all coming back to us. What multiplies to be 3 that could add to be negative 4? Start with what multiplies to be 3. Okay, 1 and 3 multiply to be 3, right? If we want them to multiply to be a positive, they have to either both be positives or both be negatives. If we need them to add to be negative 4, both negatives, you remember the factor now, right? Thinking, oh yeah, I tried to forget it, but it keeps coming back, doesn't it? We're going to use factoring this chapter, folks, okay? Because we're definitely going to use it in the second half of the chapter too. Okay, so we have factored that. Now, the question is, are there any factors that can cancel and reduce? On top, I have an x plus 3. Is there an x plus 3 on bottom? No, it's close, right? But are x plus 3 and x minus 3 the same? No, they have to be identical to cancel. On bottom, I have x minus 1 and x minus 3. Are either of those on top? No. So does anything cancel? Nothing? Excuse me. Nothing cancels. So since nothing cancels, there are no holes. Okay. So I'm going to say none. And I'm putting here in parentheses, no factors cancel. Okay, so there was step 1. We checked for holes. Step 2, what were we supposed to check for after holes? Supposed to check for vertical asymptotes, right? Okay. Flip back to that front page of the notes, right? When I flip back to this front page of the notes, what did it say about vertical asymptotes? How do I find vertical asymptotes? Setting the denominator equal to 0. Okay. So, you have two options. You can set the original denominator equal to 0, or you know what I like better? The factored denominator equal to 0. We've done this. If I set my denominators equal to 0, so if I set x minus 1 equal to 0, and x minus 3 equal to 0. Actually, well, shoot. Here, I'm going to put in right above that. You can put it below if you want. Denominator equal to 0. So x minus 1 equals 0. X minus 3 equals 0. No hard math here. How do I solve these? If it's x minus 1, we're going to add 1, right? So if we add 1, this is x equals 1. If we add 3, this is x equals 3. So, what are my vertical asymptotes? X equals 1. X equals 3. having done this right here, are there going to be any points of discontinuity on this graph?
Yeah.
So I'm backtracking again, right? Where do points of discontinuity happen? At vertical asymptotes and at holes. Do we have any vertical asymptotes or holes? Yes, we have vertical asymptotes, don't we? So are there points of discontinuity? Yes, there are. So yes, there are points of discontinuity. And where are these points of discontinuity at? At 1 and 3. Are these removable or non-removable points of discontinuity? You go back to the previous page, right? Vertical asymptotes are non-removable. So these are non-removable points of discontinuity. Am I making sense there? That's straight from my notes on the previous page, right? Flip back and forth. So I'm just trying to prepare you that they're going to ask that in homework. And if you have vertical asymptotes or holes, there are points of discontinuity. Okay, we checked holes. We checked vertical asymptotes. Now we have to find any horizontal asymptotes. So, horizontal asymptotes, did you flip back to remember? What did it say about horizontal asymptotes? Found by analyzing the biggest powers on top and bottom. So your highest exponent terms. Okay. What were my biggest exponents? What's the biggest exponent on top? The x to the first term, right? What's the biggest power on bottom? X to the second. So right here, we're thinking about x to the first over x to the second. Where is the bigger power? On bottom. What do my rules say when the biggest power is on bottom? Y equals 0, right? Straight off. Biggest power on bottom, y equals 0. So, biggest power on bottom, y equals 0. And don't be afraid to write yourself a reason in your notes. I'm writing it right here. Biggest power on bottom. Now, we're not going to be doing B. And originally in this lesson, that's all we needed to do was holes, vertical, and horizontal asymptotes. As the years, they've added a little more content here. We're going to, before we move on to the next problem, talk about domain, x-intercepts, and y-intercepts. So I'm going to use this space over here. Domain. What's my domain look like? It's going to be all reals except any vertical asymptotes or holes. Did I have any vertical asymptotes or holes in this problem? I did, didn't I? So what am I going to say here? Yep. All reals except x equals 1 and x equals 3. Or I guess you could say comma.
Can you do it as like a pair?
You wouldn't want to use an ordered pair. You could say like x equals 1 comma 3. But like I wouldn't put parentheses around that. That's just x, it's a list of numbers, not. Did it? Okay. Yeah, Math Excel, they'll give you the form there. Okay, besides domain, I said what? X-intercept. Did you flip back to the front page again? Or are you just waiting for me to tell you? You're writing, okay. X-intercepts happen. Especially it's when y equals 0, but easiest thing to do is when your numerator equals 0. What's my numerator? X plus 3. So I'm going to do my numerator equal to 0. So I'm going to set x plus 3 equal to 0. What do I do if I set x plus 3 equal to 0? Subtract 3. Big hard math here. If I subtract 3, we're going to get x equals -3. So this graph will cross the x-axis at -3. And finally, a y-intercept. What did it say to do for y-intercept?
Put 0 in for x.
Okay. Let x equal 0. So that means take either your original equation or your factored equation, either or, put 0 in for x. So if I say y equals 0 plus 3 over 0 squared minus 4 times 0 plus 3. Do the math, right? 0 plus 3 is 3. The 0 squared is 0. 4 times 0 is 0. Plus 3 is 3. What's 3 over 3? 1. What is my y-intercept? 1. I just realized I just wrote my y-intercept as 1. If I had to guess, they're going to want an ordered pair, aren't they? What's an ordered pair for if y equals 1? 0 goes in for x. So they might want you to say 0, 1. I don't require that, but they might. Same thing up here on x-intercept. If it's an x-intercept, they're going to put -3, 0. So you might have to do ordered pairs there. I don't know. I can't remember. Okay. Now, real quick, and then I do want to get another example in, but I kind of want to try and show you this on the calculator. Okay. If I type this in on the calculator real quick, what was it? X plus 3 over x squared minus 4x plus 3. Right? I want you guys to kind of see all that stuff we just talked about should make some sense here. Okay. Think about all the stuff we talked about. Can you see vertical asymptotes happening at x equals 1 and 3? They're not drawn in there, are they? But can you see the graph going up to the left of 1, up to the right of 3, and then that little upside down parabola between 1 and 3? That's indicating there's asymptotes there. Horizontal asymptote. Can you see my graph running along the x-axis? Okay. X-intercept. Kind of hard to tell, but can you see the graph crossing the x-axis at -3? We'd have to zoom in some to do some, checking, but it does. Y-intercept, can you see the graph crossing the y-axis at 1? All this stuff is valid stuff. Okay, that's what I wanted you to see, that the features do become graphs there. Okay, my other plan, I'm not sure where the time's gone today, is to do C. We'll see if we can get through everything on C. I don't know if we can or not. I don't know. How quick can I go? Probably not quick enough. First question we ask ourselves is what? Are there any holes? Now, before I can check holes, this needs to be factored. Okay? Gotta go back to first semester Algebra 2, or Algebra 1 if you want. The denominator of x minus 4 is x minus 4. My numerator. Well, guys, guess what? It factors into two parentheses. X squared breaks into x times x. What are my options to multiply to be 4? 1 and 4 or 2 and 2? How could I possibly get a 3 out of those? It's going to have to be some combination of 1 and 4. If it multiplies to be a negative, one of those numbers is positive, one of them is negative. If it adds to be negative 3, you're going to want the larger number negative, so it's negative 4 plus 1. What just happened? Do I have a factor that cancels? What's on top that's also on bottom? X minus 4. Okay, what do you get when you set x minus 4 equal to 0? So this is because x minus 4 cancels. When you set x minus 4 equal to 0, what do we get? X equals 4. So guess what? There is a hole at x equals 4. That's an at symbol there. Sorry, kind of came out crazy. Is there a point of discontinuity here? Yes. What kind of point of discontinuity is a hole? Right, removable. So this is a point of discontinuity, and specifically it is a removable point of discontinuity because it is a hole. Okay, here's an example of why we do holes before vertical asymptotes. Vertical asymptotes, you're supposed to set your denominator equal to 0. What just happened with our denominator? It canceled and was a hole. You can't have a vertical asymptote and a hole at the same place. So, because x minus 4 represents a hole, there are no vertical asymptotes. And why are there no vertical asymptotes? Because there was a hole at x equals 4. So I'm going to say there was a hole at x equals 4, and it's a vertical asymptote or hole, not both. Got it? Vertical asymptote or hole, not both. That's the note you might want to make to yourself. Horizontal asymptote is all about the powers. What's the biggest powered term on top? X squared. What's the biggest powered term on bottom? X. Where is the biggest power? On top. So what's the rule say? There are no horizontal asymptotes. And there are no horizontal asymptotes because? Right. Bigger power on top. Okay, guys. I at least got through the holes and asymptotes here. And to me, that is the harder stuff. Now, officially, yes, we should do domain, x, and y intercepts on this one, but I'm out of time, as you know. Yes, I want you to go in and work on the homework for Monday and try it. I've given you all the information. It's just applying it and using it. So see what you can do. Come back with any questions on Monday. Okay?